The James Webb Space Telescope, JWST, is mankind's most recent enormous eye, connecting across impossible distances and catching light that has traveled for more than 13 billion years. This light, however, tells us more than just a story of time. It reveals the evolution of our universe, shaped and expanded by its continuous extension. As we peer back at the most distant galaxies, we are essentially seeing an ancient era, moving increasingly close to the commencement of the universe. The Big Bang, the theory of how things came to be, a fundamental story of modern cosmology, suggests that our universe had a specific beginning and is finite in age. Yet, from its inception, this singular cosmic origin has been met with skepticism, and challenges to its validity persist even in mainstream cosmology. For decades, the Big Bang theory held strong, especially after the discovery of the cosmic microwave background CMB in the 1960s. This background radiation, a faint universal hum across the universe, perfectly aligned with predictions of a hot, dense early universe. However, crucial observations by the JWST in recent years have cast doubt and raised new questions about the Big Bang's authenticity. Through the stunning clarity of the JWST, NASA's cosmic time machine, we've seen clusters of ancient galaxies far larger and more numerous than expected, challenging our understanding of the universe's earliest stages. As the telescope peers back to when the first galaxies formed, it offers humanity a unique view, one that the Hubble telescope couldn't fully reach. Hubble was simply not sensitive enough to detect the faint, red-shifted light of these earliest galaxies. But with JWST's cutting-edge capabilities, we're looking as far back as possible, extremely close to time itself. As we venture into this unknown region, we encounter a long-standing mystery. How did the first galaxies truly form? And does the universe, as we know it, really have a single, definitive beginning? The earliest universe was a hot, foggy place, so dense that light itself couldn't freely travel. This means that, no matter how powerful our telescopes, we can't observe any further back with light. However, we are not limited to light alone. New technological advancements are opening the door to the detection of gravitational waves from colliding black holes, which could serve as a new avenue to peer back into the universe's infancy, perhaps even into the very singularity we call the Big Bang. The roots of the Big Bang theory and its growing suspicions stretch back to the 1920s and 1930s, when astronomers first observed that distant galaxies appeared to be moving away from us. This discovery, combined with Albert Einstein's theory of general relativity, set the stage for the Big Bang model. Einstein's equations predicted that a static universe would be unstable, requiring either contraction or expansion. Observing this expansion suggested that galaxies must have been closer together in the distant past, implying an explosive beginning for the universe. The universe's expansion has several major implications. Not only do objects move farther apart, but the light emitted from them stretches, shifting to longer wavelengths over time. Since wavelength corresponds to energy, with shorter wavelengths being more energetic, this redshifting means the universe has been cooling as it ages. By rewinding this cosmic expansion, we reach a point where everything would have been so hot and dense that neutral atoms couldn't exist, leading to a uniform, white-hot glow. This glow was confirmed in 1964 when astronomers Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, a pervasive radiation field faintly echoing the universe's fiery beginning. Yet, as the JWST pushes the boundaries of cosmic observation, scientists are discovering features in the early universe that strain the traditional Big Bang narrative. We see vast, luminous galaxies where there should be none, clustering in ways that defy expectations. So, if the Big Bang theory alone doesn't explain these anomalies, what else could? At the core of the Big Bang theory lies a singularity, a point of infinite density and temperature where the laws of physics break down. This is where space and time supposedly begin. But this concept, while powerful, has limits. Imagine trying to describe the entirety of existence compressed into an infinitely dense point. This is where our understanding hits a wall. Despite many aspects of the Big Bang model being supported by observations and laboratory experiments, this initial singularity remains a paradox, raising the question, could the universe have had a different kind of beginning? In its quest to understand the universe, science has found ways to recreate similar conditions. Quark-gluon plasma, for example, has been synthesized in labs, and matter-antimatter pairs have been produced to align with early universe predictions. Through these experiments, and by analyzing fluctuations in the cosmic microwave background, we have a well-supported picture of the universe's development. However, significant mysteries remain. For example, if all regions of space were once packed into a single point, why do we observe such uniform temperature across the universe? By conventional models, areas of space should show varied temperatures, as they couldn't have exchanged energy or information in such a short time. Moreover, we might expect to find remnants from the hottest epochs, such as magnetic monopoles or spatial anomalies, but none have been observed. These inconsistencies open the door to new possibilities. Either the universe inherently had these balanced properties from the beginning, or some mechanism imposed these conditions. One candidate explanation is cosmic inflation, a rapid expansion hypothesized to have occurred before the Big Bang itself. On December 7, 1979, physicist Alan Guth proposed a revolutionary idea. Before the hot Big Bang, the universe experienced an extraordinary expansion. This inflationary phase could explain why the universe appears flat, homogeneous, and isotropic. After inflation, the universe would transition into the hot, dense state associated with the Big Bang, paving the way for galaxies, stars, and planets to form. However, even cosmic inflation doesn't resolve every inconsistency. For example, groundbreaking observations by the JWST have revealed surprisingly massive galaxies from the universe's infancy, suggesting a faster growth rate than inflation alone can explain. The JWST's astonishing capabilities offer humanity a unique glimpse into the universe. This $10 billion infrared telescope has captured breathtaking images of the early universe, revealing a plethora of massive, luminous galaxies from when the universe was only a fraction of its current age. Astronomers previously believed they had a solid understanding of how matter coalesced to form the first stars and galaxies, but the JWST's findings suggest a much faster evolution than anticipated. These observations have sparked excitement and caution among scientists, as some theorists are forced to revisit key assumptions about cosmic formation. According to astrophysicist Erica Nelson, the massive galaxies observed within the first 500 million years of cosmic history defy existing models. The JWST's preliminary findings indicate that galaxies in this early epoch may be far more massive and numerous than previously thought, potentially housing masses comparable to today's giant galaxies like the Milky Way. This rapid growth challenges current cosmological models, which propose that a galaxy of such size wouldn't form until 1 to 2 billion years after the Big Bang. Nelson's research suggests that galaxies might be evolving more aggressively than expected, prompting the possibility of new theoretical frameworks for cosmic evolution. Dark matter, an invisible and mysterious substance thought to make up about 85% of the universe's mass, is believed to shape the large-scale structure of the universe. Conventional cosmology suggests that galaxies form within massive halos of dark matter, which gravitationally pulls in normal matter, allowing stars and galaxies to coalesce. However, JWST observations challenge this model, as galaxies appear to be forming in ways that defy our understanding of dark matter distribution. The presence of dark energy, an equally elusive force responsible for the universe's accelerated expansion, further complicates the picture. Some models suggest that early dark energy, a temporary boost in dark energy density, may have accelerated galaxy formation, aligning with the JWST's findings. However, such adjustments must fit within the broader framework of the standard cosmological model, which has successfully explained large-scale cosmic development. As compelling as the Big Bang theory is, it's not the only explanation for the universe's beginnings. Several alternative theories have gained attention, each offering unique perspectives. 1. The steady-state theory. Unlike the Big Bang, this theory proposes a universe without a beginning, where matter continuously appears as the universe expands. This theory suggests that as galaxies move apart, new matter is generated, maintaining a uniform density. However, it failed to account for the CMB, which strongly supports a hot, dense early universe. 2. The mirror universe hypothesis. A more speculative idea posits that two universes were born in the Big Bang, one moving forward in time and the other backward. This twin universe would evolve in reverse, providing a mirror reflection of our own cosmic history. Though highly theoretical, it suggests that the universe could be more complex than previously imagined. 3. The simulation hypothesis. This concept raises the possibility that our universe is a simulation created by an advanced civilization. Quantum entanglement and the peculiar nature of space-time lend some conceptual weight to the idea, though it remains unprovable. 4. Cyclic models. Some cosmological models suggest a universe that undergoes endless cycles of expansion and contraction, eliminating the need for a singular beginning. These models propose that the universe could have experienced a big bounce rather than a single Big Bang event. Despite the intriguing possibilities offered by these alternative theories, the Big Bang model remains the most widely accepted explanation for the universe's origin due to its strong observational support. The cosmic microwave background CMB, the large-scale structure of the universe, and the observed abundance of light elements like hydrogen and helium all align closely with predictions from the Big Bang theory. However, the discoveries made by the JWST push the boundaries of this model, forcing scientists to reconsider aspects of cosmic evolution. For example, the telescope's ability to detect galaxies that are far more massive and mature than expected challenges the timeline established by standard cosmology. This suggests that star formation and galaxy assembly may have occurred much earlier and more rapidly than previously believed. Unanswered questions and future prospects. The JWST has only begun its mission, and its future observations could reshape our understanding of the universe's origin and evolution. Several pressing questions remain. How did the first galaxies form so quickly? Current models suggest that galaxy formation should be a gradual process. Yet, the massive, fully formed galaxies observed by JWST shortly after the Big Bang challenged this notion. What role did dark matter and dark energy play? If dark matter and dark energy influenced the early universe differently than expected, they might help explain the anomalies seen in early galaxy formation. Is the universe finite or infinite? The question of whether the universe has a definitive beginning or exists within an eternal cycle remains unresolved. What lies beyond the observable universe? The universe we see is limited by the speed of light and the age of the cosmos. What exists beyond that boundary is a mystery that even the most advanced telescopes may never answer. A new era of discovery. The James Webb Space Telescope has opened a new era in our exploration of the cosmos. Its unprecedented capabilities allow us to look deeper into space and further back in time than ever before. As its mission continues, it may reveal secrets that challenge not only the Big Bang theory, but also the very foundations of modern cosmology. While the Big Bang model has served as a cornerstone of scientific understanding for decades, science thrives on challenges and new evidence. The JWST's discoveries remind us that the universe is more complex, mysterious, and awe-inspiring than we ever imagined. As humanity continues its quest for cosmic understanding, the answers we seek may redefine our place in the universe, and perhaps even rewrite the story of how everything began.